Hello students, in last lecture we have studied the concept of function, its domain, codomain, range of functions. Today we will see some properties of function. So in that first we will take first theorem. If f from a to b is function, xy are subsets of b, then inverse image of union of two sets equal to union of their inverse images, and second one is inverse image of intersection of two sets is equal to intersection of their inverse images. So to prove equality of two sets, we have to show that both are subsets of each other. So to prove first one, we will show that left hand side is subset of right hand side is subset of left hand side. Okay. So for showing left hand side is subset of right hand side, so take A belongs to F inverse of X union Y. This implies f of a must lies in X union Y. Therefore, f of a belongs to X or f of a belongs to Y by definition of union. Therefore, a belongs to f inverse X or a belongs to f inverse Y. As I am taking inverse image of f of a just, so it's inverse image of f of a, which a is also in f inverse X. Therefore, a belongs to f inverse X union f inverse Y. And as this holds for any arbitrary element a, means for any a belongs to f inverse of X union Y. This implies f inverse of X union Y is subset or equal to f inverse X union f inverse Y. Okay, we'll take this as 1. Again, we'll take element from right hand side. Let a belongs to f inverse X union f inverse Y. Therefore, a belongs to f inverse X or a belongs to f inverse Y just by using definition of union of two sets. Therefore, f of a belongs to X or f of a belongs to Y. Is it clear? Means f of a belongs to X union Y. This implies a belongs to f inverse X union Y. And this a is arbitrary from f inverse X union f inverse Y. And therefore, f inverse X union f inverse Y, this must be subset of f inverse X union Y. From 1 and 2, we get equality. Okay. So from 1 and 2, f inverse of X union Y is equal to f inverse X union f inverse Y. Okay. Now we'll prove second one. Again, for that we'll do same thing. Second, let a belongs to f inverse of X intersection Y. Therefore, this arbitrary choice, f of a belongs to X intersection Y. By definition of intersection, f of a lies in both of sets. Therefore, f of a belongs to X and f of a also belongs to Y. This implies a belongs to f inverse X and a also belongs to f inverse Y. Therefore, a belongs to f inverse X intersection f inverse Y. For every a belongs to f inverse X intersection Y, because choice of a is arbitrary. I am not taking any restriction on choice. So it represents arbitrary element. This implies f inverse of X intersection Y is subset of f inverse X intersection f inverse Y. Again, for this second, we'll take this as 1. Now for A belonging to F inverse X intersection F inverse Y, A belongs to F inverse X and A also belongs to F inverse Y by definition of intersection. Therefore, F of A lies in X and F of A also lies in Y. As F of A lies in X, it lies in Y. Therefore, F of A belongs to X intersection Y and therefore A belongs to F inverse of X intersection Y. For any A belongs to F inverse X intersection F inverse Y and therefore F inverse X intersection F inverse Y is subset of F inverse X intersection Y. So from 1 and 2, equality hold means F inverse X intersection Y is equal to F inverse X intersection F inverse Y. Now again, if F is a function from A to B and XY are subsets of A, then what is the relation between their images with respect to union and intersection operation? So the proof is also completely differs. I cannot make changes there. So first, then F of A union B is equal to F of A union F of B. Second, F of A intersection B is subset or equal to F of A intersection F of B. Moreover, equality hold if and only F is 1-1 function. If F is not 1-1, then equality doesn't hold. Okay, so we'll prove this. 1. So to prove that, first we have to show that every element of left hand side lies here and every element of right hand side also lies in left hand side. Okay, so let B belongs to, here we'll take X intersection X union Y is equal to F of X union F of Y, F of X intersection Y is equal to F of X intersection F of Y. Equality hold if and only that hold. So let B belongs to F of X union Y. I am taking B symbol as it lies in F of X union Y. X union Y is subset of A, its image is subset of B, and so I am taking notation of element from B set. Is it clear? So B is member of F of X union Y. As it lies in union. So here I cannot take F inverse B symbol now. I cannot take F inverse B. B is image of some element of X union Y. Implies there exists some A belongs to X union Y such that F of A is equal to B. F of A equal to B. B lies in image of X union Y set, so it has pre-image in X union Y. That set may have more than one pre-image, so I cannot use just F inverse B symbol. F inverse B is not element, it may be set. If it is one function, then it is just single element, and then in that case I can use F inverse B symbol. But if it is not 1-1, that particular element may have 2 pre-images, 3 pre-images, or infinitely pre-images. Also, if I take the constant function C, then If I take element from x union y, f of x union y, and that f of x union y contain that constant, then its inverse image of B contain all elements from domain set, and then it becomes whole set A. That's why don't use symbol F inverse B belongs to x union y. That is the incorrect notation. That is incorrect notation. F inverse B is subset of x union y. F inverse B is subset of x union y. Remember this carefully. Okay, students are making mistake here in this step. Okay, f of A is equal to B. Therefore, A belongs to x or A belongs to y implies B equal to f of A belongs to x or B equal to f of A belongs to y. Okay. Is it clear? Sorry, f of x, f of y. So, f of A which is equal to B lies in f of x or f of y. This implies B belongs to fx union fy. For any B belongs to f of x union y, because this choice of B is arbitrary, this implies f of x union y is subset of f of x union f of y. Give one for it. Again, take element from right hand side. Okay. Now, let B belongs to f of x union f of y. This implies B belongs to fx or B belongs to f of y. Implies there exists A1 belongs to x or A2 belongs to y, such that f of A1 is equal to B belongs to fx, or f of A2 is B belongs to f of y. Implies there exists A equal to A1 or A2 in x union y, such that f of A equal to B belongs to f of x union y. So, if there are two premises, then I can take A equal to A1 or A2. F of A equal to B lies in f of x union y. This implies B belongs to f of x union y for every B belongs to fx union fy. Therefore, fx union fy is subset of f of x union y from 1 and 2 one fold. From 1 and 2 one fold. 1 and 2 f of x union y is equal to f of x union f of y. Now we'll prove second part on same line. So let B belongs to f of x intersection y. This implies there exists some A belongs to x intersection y, such that f of A is equal to B, f of A equal to B. Implies A belongs to x and A belongs to y, is such that f of a is equal to b belongs to fx, and f of a is equal to b also belongs to f of y. F of a lies in fx, f of a lies in y, but f of a is precisely b, so b lies in fx intersection y. This implies b belongs to fx intersection fy. For any b belongs to f of x intersection y. This implies f of x intersection y is subset of f of x intersection f of y. Now, equality may not hold. For that, I have mentioned that equality hold if and only if f is 1, 1 function. So, to prove equality doesn't hold, okay, equality fails for arbitrary function f. We have to give some counter example, okay. So, note, if f from x to r or r to r is function such that function defined as fx is equal to q or fx is equal to k for all x belongs to r, then f of q intersection q complement. What is q? Set of rationals. What is q complement? Set of irrational. Their intersection is empty set. So it becomes f of phi is equal to phi set. F always map empty set to empty set. And f of q intersection f of q complement is equal to singleton k intersection singleton k, which is equal to k. Okay, fx is constant function. Okay, this implies f of q intersection q complement is not equal to f of q intersection f of q complement. Constant function is not 1, 1. So if you take any function which is not 1, 1, then you can construct the two subsets such that image of intersection of two sets is not equal to intersection of their images. It is always possible if f is a not 1, 1 function. But over that x intersection y, if that f is 1, 1, then equality holds that. Okay. If your choices of subsets x and y are in such a way that over that part x intersection y, f is 1, 1 function, then equality must hold there. Okay. Means just by taking that x and y sets in such a way that their intersection, over that intersection f remains 1, 1, then equality must hold by that result. So you have to choose sets in such a way that over that x intersection y, in that x intersection y, you must get at least two different elements having same image, and then with help of that you can construct example where equality doesn't hold. Okay, so we have to prove if f is 1, 1 function. Okay. Now, if f is 1, 1 function, then to show f of x intersection y is equal to f of x intersection f of y. So for this, it is sufficient to show f of x intersection f of y is subset of fx intersection y. Because for arbitrary function, this inequality hold, this inclusion relation hold. So for 1, 1 function also that hold. So one way inequality is proved, even the function is not 1, 1. Now if f is 1, 1, we have to use that to show this hold. Okay, so let B belongs to fx intersection f of y implies B belongs to fx and B also belongs to f of y. Implies there exists some a1 belongs to x and a2 belongs to y such that f of a1 is equal to f of a2 is equal to b. Now f is 1 function implies 1 function, therefore f of a1 is equal to f of a2 implies a1 is equal to a2, and therefore a equal to a1 is equal to a2 belongs to x intersection y is such that f of a is equal to b, which belongs to f of x intersection y. So a1 and a2 both are equal by definition of 1 function. Okay, this implies b belongs to fx intersection y for every b belongs to fx intersection f of y. Therefore f of x intersection f of y is subset of f of x intersection y. So, and therefore fx intersection y must be equal to fx intersection f of y if f is 1 function. And if it is not 1 function, then I have given the counter example where equality doesn't hold, means this theorem is true if and only if equality hold if and only if f is 1 function. So today we have studied the important properties of function. With this discussion, we will stop our lecture. In next lecture, we will study concept of equivalent sets, and we will use that equivalent sets to define concept of countable sets. Thank you.